Howdy, my name is Gavin Lukasik, and I'm a PhD student in the Optical Diagnostics and Imaging Laboratory at Texas A&M. I want to thank you for attending my presentation on the application of digital particle tracking in Schlieren imaging to study debris cloud and shockwave formation during hypervelocity impacts. Here's an outline of my presentation, and at this time, I would also like to thank the Army's Future Command for funding this research. Hypervelocity impact studies are important in a number of fields. In order to design effectively for these applications, though, complex computational models are needed to explain the material behavior effectively. In order to do that, we need to produce validation data that can be put against these models to prove that they are effective. And traditional diagnostics are just not great at handling the speed and energy of these events. However, novel optical diagnostics may be the answer to bridge that gap and provide critical model validation data. In this work, we're going to look at megahertz rate Schlieren imaging and advanced particle tracking methods to understand shock physics and fragment behavior and hypervelocity impacts. Specifically, we're going to focus on polyethylene hypervelocity impacts. Because polyethylenes are lightweight and can dissipate large amounts of energy, they could be a prime candidate for hypervelocity protection structures. We're also going to look today specifically at ultra-high molecular weight polyethylene sheets impacted with aluminum spherical projectiles. The video shown here is the ultra-high molecular weight at 2.6 kilometers per second. And I've also included some frames just to show the debris cloud evolution. The videos that we're going to see later in the presentation are very, very similar to these conditions as well. To perform these hypervelocity impact experiments, we use a two-stage light gas gun at Texas A&M's Hypervelocity Impact Laboratory, directed by Dr. Thomas Lacey. The gun is capable of accelerating projectiles of 4 to 10 millimeters in diameter of a variety of shapes and materials up to speeds at 2 to 8 kilometers per second. We're also able to shoot a variety of materials, including polymers, such as this case, metals, ceramics, composites, and even geomaterials. Some of the current diagnostic capabilities that we are implementing, mainly the Shimadzu HBV X2 high-speed camera with a 250 by 400 pixel array, capable of frame rates of up to 10 million frames per second. However, we commonly operate at 1 million frames a second. One of the first things that we implemented in the lab was a dynamic delay generator. Because of the extreme speeds, we needed something that set a variable delay based on the velocity, and the dynamic delay generator does exactly that. It takes in a real-time velocity, calculates the delay, and sends the output trigger to the diagnostic equipment. We also applied Schlieren imaging, which I'll talk about on the next slide. And in the future, we are going to apply laser-based and X-ray diagnostics as well. So here's our Schlieren imaging apparatus. We have two large lenses that collimate the beam through the test area. We have a high-powered amber LED that's powered at 3 volts, 1 to 25 amps DC. We actually ran the light at 1 amp and found that that was sufficient for our work in this case, but we do want to go to higher brightnesses to increase our sensitivity. We've included a 50 millimeter diameter negative lens that helps with focusing issues. And the last piece of optics is a 50 millimeter camera lens that's attached to the Shimadzu camera. You can see from the schematic that we've actually moved the system slightly downrange to look at the backface debris cloud as opposed to kind of straddling the target. This is because of the zoom of the system, and we just really want to see the particles when they're dispersed and not just the debris cloud as it's kind of expanding and it's a big shadow. And so here's the results from our Schlieren experiment. And like I said earlier, this is a really similar condition, 2.5 kilometers per second, aluminum sphere, 10 millimeters. It's ultra high molecular weight. The only difference is that the backfill is slightly higher. It's, I think, 300 torr of nitrogen. And so from these videos, we can see some really interesting things popping up, especially when you compare to the non-Schlieren. When you look at the leading edge, you can see an interesting cone-shaped bow shock that forms kind of around this cloud of particles. And the cloud of particles is present in both. However, the bow shock is really interesting in how it develops and travels with the leading edge of the debris cloud. You also see individual bow shocks on all of the different particles in the debris cloud especially as they start to disperse. And at later points in the video, you start to see shock-shock and shock particle interactions as well. So now for digital particle tracking, there's really two main steps to break it down into: segmentation and then grouping and pairing. Segmentation is just separating the particles from the background. And we did this through 3 steps. To start, we compared the video to a calibration frame with no particles present. If the pixels were similar, then we could assume that that was a background pixel and we could eliminate it. If it was not, then it could have been a particle. We then applied a low threshold to remove small variations that squeaked through the first step. And then we ended with an iterative thresholding process that checked the maximum variation among pixels in the frame and iterated until that value was acceptable. And so the binary video is actually shown in the bottom left, and 2 frames from that video are shown in the bottom right for comparison. And you can see that visually it looks like the code did a pretty good job of actually segmenting out even some of the smaller particles and in harder to see areas. After segmentation, we go to grouping and pairing. So we have this binary image. We take all of the particle pixels, so the bright pixels on the background, and what we do is, based on how many neighbors they have that are also particle pixels, we can group those together into particles. Once we have our particle pixels grouped together, we can calculate the size and the coordinates of the center of that particle based on all of the pixel locations in that particle. From there, we can compare that frame by frame to pair. So what we do is we compare the straight line distance of a particle in one frame to that in another, and we also compare the difference in size of the 2 particles. When this value is minimized, we can say that we have a pair because the particle is in close proximity to a particle in the next frame and relatively close in size. So the left 2 images show the ability to pinpoint the particles, and the right image the video shows the ability to track the particle frame by frame by frame. So what we do with the particles after we pair frame by frame is actually group them into trajectories. So we pair all of the particles that match in one frame and try to see if it matched in the next frame, and so forth and so on, until we get these really long trajectories. We've plotted those trajectories in the videos, and you can see that we get some pretty long lines showing that it effectively tracks some particles for really long durations of the video. One of the last steps we performed in the particle tracking was zooming in to a specific particle and kind of following it with our frame of view to see what was happening at a smaller scale. So we chose this particle in particular because we saw it kind of start to break up and doing some interesting spinning. But this can actually be applied to any particle that we tracked for, a number of frames. And, we just zeroed in on a window and tried to blow up that view to really see what's going on. And we really look forward to seeing how we can apply this to future applications, 3D methods, to really get a lot of interesting information, out of these videos. So in summary, digital particle tracking methods were applied to back out the velocity and size of particles using 2D hypervelocity impact videos. Future versions will involve trying to find orientations, spin rates, and as much other particle information as we can try and get out of the video. We also looked at shock structure using high-speed Schlieren, and from this, bow shock was really clearly visible around individual particles in the debris cloud. And this is interesting not only for the physics aspect, but also because this has to be taken into account when we are designing our future holographic-based particle tracking methods. So in the future work, we're going to apply other forms of illumination. So we mentioned laser illumination earlier. We're going to try and improve our own LED illumination that we have currently. And finally, we're going to try and test a variety of materials, projectile speeds, and pressures to just really get a good idea of how far we can apply these methods. Thank you for your time.